Okay, so thanks everyone. My name's Shayne Flint. I'm a lecturer here at the ANU in software engineering. I run the software engineering program for those that don't know. And I'll be talking today with Damien Beard, who's one of our undergraduate students, third year software engineering student. And we'll be talking about software engineering education, but more specifically about the role of systems thinking in software engineering. So this gives you a bit of an idea of what we're going to talk about. I'm going to give you a bit of an overview of what systems thinking is. Is anyone familiar with the term systems thinking? Or, I know Ben should know. And, Emily. So I'll give a bit of an overview of what systems thinking is, and then I'll hand over to Damien, who will talk about how he sees systems thinking within the context of studying software engineering and how it might apply later on. We'll talk a little bit about a course that we introduced here at the ANU last year, and we've run it this year for the second time, and we'll give you an opportunity to ask some questions. So traditionally when we think about complicated systems, we tend to try to understand them by pulling them apart, right? We pull the car apart, we look at all the bits and pieces, and we try and make sense of what those bits are, how they're made, how they fit together, so the interfaces between these things, and we try to build up a picture of what the car is. But what this sort of reductionist or analytical thinking doesn't give us is the ability to answer questions such as this. You know, why does this car have 4 seats? When we can study it, we can see, yeah, it's got 4 seats, they're made of leather and steel and stuff, but it doesn't tell us anything about why there are only 4 of them. Why not 10? Why not 1? It doesn't tell us anything about why it happens to be painted red. Or in fact, for that matter, why it's painted at all. Why not just drive around in bare steel car? A more interesting one is, why is the steering wheel, in this case, on the left-hand side? Why not on the right-hand side? Why not in the middle? So this reductionist approach or analytical approach to thinking can tell us a lot about the car, but there are some other important questions it can't answer. And that's why we want to use why the idea of systems thinking has emerged. So, as it says there, we cannot fully understand the car using reductionist thinking. It tells us what about the car. It answers questions of what things are involved in the internal connections, but we need another way of thinking in order to focus on the why. In other words, external connections, as we'll see shortly. Now, systems thinking's been around a very long time. I've got some references or some resources at the end. It emerged during the Second World War, became a really hot topic in research and even in industry in the sort of 50s and 60s. And that sort of died off for a while and wasn't really, sort of not much attention was paid to it for a very long time until maybe the last 10 or 15 years where it started to come back. Okay, so let's think about why the car might have 4 seats. Well, it has 4 seats because cars are typically used by families for short trips. So families, usually 4 or 5 people, going from A to B. There's no need for them to drive around in a double-decker bus, right? Mostly a 4-seat vehicle will do the job. So it's a connection between the car and the context within which it's used that helps us answer that question about why it has 4 seats. Any amount of analytical thinking or reductionist thinking about the car will not answer that question. In the case of painting a car, well, first thing is, I guess, is that cars are kept and usually operated in adverse weather conditions, so rain, storm, that kind of thing. So they're painted in order to protect them, stop them corroding. There's a purpose for the painting, which is about the context within which the car is operated. If the car was being operated within indoors, then you may not need to paint it. The colour has a lot to do with the marketing, the promotion, what people want. Customers prefer one colour over another, so the car suppliers tend to provide a range of colours. But again, you would never be able to answer that question by just looking at the car. If you just looked at that picture, it couldn't tell you why the car is red or why it's painted. When it comes to steering, these are American photos. I couldn't find Australian photos, but the reason the steering in America is on the left-hand side of the car is because that gives you the best line of sight to oncoming traffic past cars that might be in front of you. So if you're driving down the road and there's a car in front of you, you want to be on this side because you can see more of the oncoming traffic than you can if the steering wheel's on the other side. So that has to do with road rules. It has to do with the wider transport system that in the US and in Europe and in Japan, cars drive on the right-hand side of the road, and it's that dictates where the driver sits. It's nothing to do with the car itself. Again, reductionist thinking will not answer that question. But when you look at the role of the car, the way the car operates within that broader system, you can start to answer these sorts of questions. And I touched on that a minute ago that in order to fully understand the car, you have to understand the role that it plays and how it interacts with the broader system of which it's a part. In the case of a car, it's part of the road transport system. And that involves the roads, other vehicles, traffic control, traffic management, the road system itself. And you need to start to think about how the car interacts with all of those things in order to fully understand the car. So, the upshot is that in order to fully understand complicated systems and even complex systems is to adopt both a reductionist approach to thinking and a systems approach to thinking. You need to have a way where you can look in, pull things apart and understand the bits, but then think up and understand the role that car plays in the bigger system. I put these in too. One of the research projects that we're working on at the moment is looking at the difference between the culture around Apple phones, iPhones, versus Android phones. And why is it that people are attracted to one or the other? And Apple, if you look at the way they go about designing things, and there's been some recent articles that some of you may be familiar with, where they focus not on features, they focus on, in the case of this spiel here, on the experience that people have with the product. In other words, what role does the phone play in the lives of its users? That's where they start. How can we design this thing? How can we structure the software? How can we organise the use of this phone in order to enhance the lives of the people using it? That's their starting point. Whereas other suppliers might focus more on the features. It's got this many pixels and this, type of processor and this much memory and blah, blah, blah. It's got an SD slot and all the rest of it, right? And then say, once we've got all those features, we can then do all these wonderful things. Whereas Apple do it the other way around. They say, well, what are the wonderful things we want to do? Then designing a system to do it. And, we suspect through looking at a lot of information out there and what people have written about Apple, that we think that internally they do take a very strong systems thinking approach to the way they develop their products. This slide I've just put up to sort of summarise my bit of it, that I work in my day job with ecologists. So I'm an engineer originally, got into computing, and more recently I spend most of my time helping people in other disciplines make use of computing, right? So, computing is an enabling discipline, so that's where I see the work I'm doing. And in ecology, there are a whole pile of aspects to that all work together to create this idea of ecological science. There's certainly high-performance computing, and there's software associated with that. There are various models, but there's also education. There's also the real world itself, natural disturbances, fire and flood and so on. And it's all of these things that interact, that constitute the system of ecology. And software is a part of that system. And you can't build good software to help ecological scientists do their job unless you build it with that systems view of understanding the role that software plays in ecology. And I can talk a lot more about that if you like later. So, hand over to Damien.
Thank you. So to start off with, looking at that example of a car and how it fits in with the system, with the roads, with the city, how it works. Software engineering students were a lot like that. We fit into a system. We come into university, we process something, which is our courses. We complete our courses and our training. At the end, we come out as a software engineer. That's the way the model looks like. So right now, when people come into university, there's a bit of a disconnect because they don't know, what does it mean to be a software engineer? Is that just a title? Is that something you can put on your business card? And I don't think that's something that's necessarily exclusive to software engineering itself. That's something that's probably across all of university. An art student coming in may not know what they are going to do with that arts degree when they finish at the end of the day. But we do have a disconnect here at the moment. When we come into university, we know we have to do these certain courses, and at the end, I'm going to get a tick that says I'm a software engineer. And that's the way that the university looks at the courses. And that's right, I think, because this is... When I log into our study out page, for those of you that don't go to ANU, this is the page that says if you're going to complete a software engineering degree, these are the courses you need to tick off. So these underlined ones are the ones that you have to complete if you want to become a software engineer at the end of your degree. So the way the university looks at it is exactly like this. It puts into a matrix and says if you can tick each one of these boxes, that means you're a software engineer. Unfortunately, though, there's a disconnect in that because the value of a system doesn't come from the sum of its parts. When we're looking at a car, just say we use the car analogy again, when you look at an engine, the value of an engine doesn't come from disassembling it and you have cylinders and valves and spark plugs, because if you disassemble it, you don't have an engine anymore. All you have are the parts of an engine. It's when you put it together, that's where you get your value from. It's not the sum of the parts, it's the product of their interaction that gives you the value of the system. So this is just a zoomed in view of that table before, and this is what it looks like for us when we go in and say, what courses do I need to tick off to become a software engineer? These courses together, this is the way it looks like. If I can tick off Comp 1100, if I can tick off Engineering 1211, that's what I need to do. Unfortunately, though, that's where the disconnect is, because we say, okay, well, I've learned what Haskell is in Comp 1100, therefore I've got that skill as a software engineer. The fact is, though, when we're going into industry, there's a disconnect because that's not what they expect from us. They're not necessarily looking at, can you program in Haskell? We haven't used that for 300 years. What they're looking at is, can you pick up a functional programming language and can you learn it in a couple of weeks and become efficient in it? And that's where the context of this comes in. That's where it comes in of us looking at ourselves and saying, why am I taking this course? Where does taking this course fit in with the wider system of being a systems engineer, a software engineer, sorry. So, and this isn't just our opinions on it. This is the culture that's in industry at the moment. So, for example, to just give you one example, a couple of days ago I googled software engineer. I just put it in Google, and the third result that came up, this is below the advertised ones, the third thing that hit my search results was an opinion piece from the Sydney Morning Herald that was titled, "Want to be a software engineer? Don't go to university." And it gives a spiel about how software engineers in universities are learning outdated languages and people don't know how to apply things and rah. I don't agree with this article, but the fact is it has enough visibility that it comes up as the third result on my Google search result when I look up software engineer. So we need to think, okay, why is this culture there? Why have people got this view? And it's because that is our view on ourselves. We're saying we learn Haskell. And so that's the skill that we're taking when we need to look at why we're learning these skills in the first place. So it's about a change of perspective, and it's an inward-facing change of perspective. As students, we need to see that we are part of the system. So if we come into university and we learn courses about algorithms and project management and programming languages, it's not the fact that we've learned all of these things in isolation that make us a useful software engineer. It's about putting those things together and learning how to thread them and use them and amalgamate those skills so that we become useful in industry or in research or wherever you want to go. And having that view, then going through, it means you're not necessarily you're busting your gut to get that Haskell assignment done the night before Because that's not necessarily the skill that you need to be working on, is, you know, making sure that you just get that thing done. It's about, have I learned how to pick up a programming language and apply it to this problem that I've been given? So it's about this change of perspective that we have on ourselves. So what can we do as students? First of all, understand the context of our degrees. So no, if I'm going to become a software engineer, what can I do with that? You know, I can be a systems architect, I can go into requirements engineering, I can go into safety systems. There's so many different areas we can go into, and going through my path at university, how can each skill I learn be applied to that outside or wherever I want to go? And understanding which skills are useful and which skills we need to be putting our efforts into to fit in with that wider context and using that systems thinking perspective on our own degree. Making links between our courses and being a software engineer. So that's just like what I was saying before. And asking the questions, you know, how does learning about this certain feature, how does learning about formal methods in software engineering help me become a better software engineer? When people are going to tell you, you're never going to use this in the workplace. Why am I learning Z? Why am I learning these things? If you can ask the why questions, you can either work out, well, you know, this is where the value comes in this, and this is why I should be putting effort into it. Or then you can question and say, well, why are we doing this? This isn't going to be giving me value. And you can actually question the system and make the system better, so at the end of the day, you have more value. The product of your interaction is greater because you understand where you fit in with the context of industry. So at the end of the day, you have this perspective that, yes, I am valuable because of the product of these courses, and that's the mathematical product of these courses rather than just the sum of putting them all together and getting the title of software engineer. So Shayne's going to have a little bit of a spiel about how we started implementing this at ANU and how we're trying to get this integrated with one of our new courses, Comp 3530.
And then Damien will talk about where he thinks we should go with this. And I happen to agree with him. So we... how many people from ANU? Again, and I know there's two of you have taken this course, right? Only two? Yeah. So this is a third-year course we introduced last year after a very long period of hounding people in the college. And with support from Engineers Australia and various other reviews saying that our software engineering degree needed to include aspects of systems engineering. So the course is Systems Engineering for Software Engineers. It starts with a couple of weeks talking about systems thinking, so the sort of stuff we've talked about here today. And we do that by having, each week we have one or two people come along. They might be academics, they might be from industry or government departments, but either way, these are people who are expert in a particular aspect of systems thinking or systems engineering. So the systems thinking talk, for example, is done by an ecologist and an engineer. We have people coming in talking about architecture and requirements and large-scale systems, human error, safety systems, those kinds of things. But it's all done within the context of this, or within this sort of systems context, as Damien was saying, making the connections. So we might be talking about something dry like, requirements engineering, but by putting it within the context of the system of engineering or within the context of building a large complex system like an aircraft or a ship, then the relevance of that subject becomes clearer to the students and hopefully becomes more engaging. I should have actually put some of the quotes that we've received from students who have done this course, and they're really quite encouraging to us that comments like, this has changed the way I think about software engineering and the way I think about my education. And that's really what this course is about. We're not expecting people to come out of this course with detailed knowledge of requirements engineering and architecture and testing and all those things, right? What we're expecting people to do is come out of this course with a different approach, with a different way of thinking about their education and their career. And I know that's happened to a lot of our students, and Damien's an example of that. Just an aside, are your videos on the web? Are they sort of publicly
Yes, they are.
Well, we'll talk about that later, but if I'll talk to Damien. But he, as part of the course, students put together a learning portfolio, and Damien every week put a little short video together, and they're really, really good. And I think they'd be useful to anyone to have a look at. So we should have a talk about maybe.
You can probably Google them. If you Google that comp course, usually you can come up with a couple of the different learning portfolios that go through it. But yeah, I have a blog that goes through 12 different subjects on that.
What else is there? Yeah, and as I said, it helps students understand aspects of software engineering, how to put these things together to solve complex problems. We weren't going to leave this slide in, but they're the sorts of things you do in the software engineering course, right? And in isolation, I find them all sort of pretty dry. That's my personal view. I don't get excited about any of those individual things, right? Except maybe modelling, if it's there somewhere. That's I do a lot of modelling. But the rest of the stuff I'm not too enthused about. But when you put it all together, it really gets exciting, right? To me anyway. I'm sure to Damien and others. This is what makes being an engineer fun, is when you can start to see how these things are connected together. Don't analyse too much the connections, right? They're pretty much random, but it's just to make a point, right? I tried to think it through. I'll give up. I haven't got time for this. Okay, so back to Damien.
Cool. So as a university, why should we care about these things? Because the reality is, if we're going to be changing the structure, adding things in, it's going to take effort. So why should we be doing this in the first place? So this, for me, really comes down to two main points. The first of all is we can produce better quality graduates, and that's something that is a high priority on any university's list, particularly here at ANU. And the reason for that is, we were talking about before, having that inward-facing systems perspective of yourself and finding out where you fit into the context of software engineering helps you, gives you motivation as you're studying, because you know, why am I doing this? It makes you learn things more thoroughly just because of the nature of where it's going to take you, rather than just learning it, crammed the night before, learning something and forgetting it the next day. So we'll make graduates that are the product of these courses that they're doing, rather than the sum. And at the end of the day, that also makes a better reputation for the university, which is something that it's a high priority for any university. The second point, though, which is probably more close to home for anyone who builds software, is that software is complex. And I mean that in the sense that software has to interact with other systems. The very nature of software is, even the most trivial piece of software sits on hardware. You can't just have software that exists by itself. And then you start introducing people into that system, into that mix. You start introducing other, like ecological factors into that. Software is complex by its very nature. And so by having this systems perspective, it can help you understand it and put that software in context. So when you're building software, say for an aeroplane, that you're not going to introduce something into your software that causes an overflow error that then causes the engines to shut down. And you make sure that what you do, you understand how what you do affects the other systems in play with that piece of software. And that's something that is really valuable, that comes out of systems thinking. That's a direct product of using systems thinking when designing software. This is a quote from Einstein: "So we cannot solve our problems with the same level of thinking that created them." I think most people would agree with that statement, but it's not necessarily a lot of people would understand what that means. So at the moment in university, we've shown you that we use an analytical view for putting our degrees together, and then we're producing graduates at the end that the industry has this perception, there's this culture, that we're theorists, that we can't use this in practice. To change this, we need to change the way we think about putting these together. And so that's why we're proposing use systems thinking, not only putting systems thinking into the degree, but using systems thinking when designing the degree in the first place. Because we already have all the parts there for a purposeful system. We are valuable when we go into the industry, but it's about maximising that value. So right now, we've already got all these parts. We have algorithms, we have formal methods, we have all these things in this diagram here. We look at mathematics, we have all these things there. It's just a matter of chaining them together. So And the other part of it is introducing systems thinking early into the degree. So there are research papers about saying that we should be introducing systems thinking as early as primary school. We should be teaching people about systems thinking so they can learn to apply that all the way through their life. Because I'm sure everyone here today now understands what is systems thinking. It's about seeing something and seeing it in the context of its environment and how it interacts. That's quite a simple thing to understand, but applying that to your life and applying that to the systems that you interact with, that is not a trivial task. So getting people introduced to it early with the expectation that not everyone's going to get it right away, but giving people the best chance. So let's introduce it earlier into our degrees and then thread it through the degree. Don't just introduce it at the start or introduce it in third year like a lot of us have experienced with. Introduce it in first year and then reinforce it as you go throughout your degree. So it's just about integrating this idea of system thinking. Let's get people on board with it. Let's give them the best opportunity to understand these things and support them the way through so that at the end of the day, you do have a well-rounded software engineer. That is what we're producing, and we can guarantee that. Rather than just a tick in the box that says, yes, I've covered all these different subjects, so I am a software engineer. Rather saying, I can do all these things, understand how they fit together, and how I can take these things that fit together and use them in any context, in industry, in research, wherever. That's what we should be aiming that box to be ticking when people are walking out the door with that cap and gown. So from the future, from this point in, let's get introduce system thinking earlier. Let's get it in early courses and bring it up again. It doesn't have to be an assessment, just teaching people, letting people learn, give them the opportunity to know about these things. Reinforce it the whole way throughout the degree program so that, people do have that best chance that we've been talking about. And let people know when they come in. Don't tell people in final year, these are the type of graduate jobs you can get, and then from there you can sit in the public service or you can sit in this private industry, this company for the rest of your life. Let people know if you want to be a software engineer and if you get these skills and if you can make this at the end of the day, these are the type of areas you can go into. It's just about giving context and giving it early. So basically that's it for me. That's where I think the university should be taking this and introducing this earlier. I don't think that it's going to take a big restructure because all the parts are already there to make a valuable system. It's just about threading them together and giving people that context about what their degree is. So here's a couple, it's a bit hard to see up there, but there's a couple of links, and this, I'm sure this, they're there, it's just very bright. Giving people, so there's a couple of resources you can go to learn more about system thinking if you're interested in it. And I'm sure these slides will be going on the web somewhere. Can I get a nod from a CompCon person? Yeah, no. This
yeah, we can. Oh, you can send it. Do you have any lecture recordings? You will be able to see the slides. Yeah.
Live on live. Anyway.
Yeah.
Well, it's actually blue on here, but
Yeah.
not to worry. But no, we'll make sure.
We're putting our papers up publicly later on.
Okay, good.
Okay, great. So these resources are online. There are plenty of things you can Google as well. I know there's a bottom link here. The one here is the Comp 3530 site that Shayne showed you before. That's the systems engineering for software engineers that is being run at the moment in third year for software engineers, and these slides will be going on there as well.
Yeah.
Is that right?
Yeah. And the other you can't see the links, but MIT, the way they do engineering now is they have an engineering systems division that sits across the management area, sociology, and science. And appointments into the engineering systems division are dual appointments. So you're appointed half in the engineering systems division and half in one of those other schools. And if you look at there's two links there. One's their basic website, but there's also a video. And that video explains from MIT's perspective, again, the importance of systems thinking and the importance of that to the future of engineering. And everything they say in that video applies to software engineering, and as Damien said, we're trying to get this culture into the ANU program. We've started with this third year course, but hopefully we'll start pushing these ideas back into first year and second year. And I think that's about it, wasn't it, Damien?
Yeah, that's all for me.
Yep.
We've got plenty of time for questions. So.
Yeah, so questions for either of us, and we're happy to talk about things around this if you like.
So you spoke about the course at ANU and how it relates to the thinking about system thinking in relation to a car, and also how it can play a part in design with iOS. But in terms of software engineering, can you go through an example of how it relates to the engineering process in software?
So this particular course is mainly about engineering in general, isn't it?
Yeah.
There's a little bit of there's a software flavour to it, but it is specifically about the bigger picture of what it is to be an engineer.
Okay.
Right? And what it is to be an engineer is to draw on knowledge from various disciplines. So typically it's scientific knowledge, but it's also management knowledge, economics, the law, sociology, psychology, any discipline you care to name pretty much. And it's about how you integrate that knowledge in order to address a problem, or at least live with a problem.
It's like a professional type of course.
Yeah. But there is technical content in it. So we do talk about requirements engineering from a software perspective, architecture or enterprise architecture, that kind of stuff. Human error. The human error, the lady that does that is actually a former Air Force pilot, so she's doing it from an aviation perspective, but is able to connect that to engineering and software engineering. She now applies that with medicine. What else do we have? We have the safety people from York University. They visit here every year. They're sort of the world experts on system safety. So they again talk about safety in a general sense, but try to connect it to software. So it's about those meta skills. It's about that culture of there's an engineering culture, and you just happen to be using software rather than a mechanical aspect or a civil aspect or whatever. I think that where software comes in is almost really just another discipline you're drawing on. It's just you happen to be expert in that, right?
I can give you an example too. A lot of these examples, because we did a couple of case studies in this course, and the examples you get are always of failures in this area. So where people haven't applied system thinking and why things have gone wrong. So one example was the woman who did human error was talking about she worked with some programmers that were designing software for the tail of a plane, and there was some issue that when it can get locked, and so they put in a safeguard mechanism that if the wind pushes it too far to one direction, that it then disengages and it then becomes, it doesn't work anymore. It just relaxes, and which they thought was a perfectly viable, safety mechanism. That piece of code was put in there for safety purposes. Anyway, in the first trial, it took like a minute or something, and people tried to take off from the plane. It was just a set of Air Force. It was a group of 7 of them, I think it was. That as soon as the plane took off, the wind came, and the reason why it worked that way mechanically in the first place, that it locked in place, there was a reason for that. The software engineers just didn't know that. They didn't understand the context of that software, why it was doing that in the first place. So they basically cut that bit out, and those people died. And another example is about hospital beds, getting people into hospital beds, and how originally there's all these pushes just to get more beds into the hospital, and trying to schedule people into hospital beds. It's a nightmare. And politically, people could just keep saying we need bigger hospitals, we need more hospital beds. And then when they built this modelling software and brought in systems thinking, so this is a positive story, when they brought in this systems thinking and they added more beds in and they used systems thinking for this modelling, they found that it didn't solve the problem. No matter how many beds they put in, it wasn't solving the problem. And the reason was because elective surgery patients were coming in and taking beds when emergency patients needed them as well. And so with that software, they said, okay, using the systems thinking that we've used in the software, we now need to apply that to the actual scheduling and the physical, putting people in beds and getting people into elective surgery and emergency surgery in the hospitals. And they use that to then improve the system. And that was something where they use systems thinking with software in a positive context to help improve a system outside of just the context of that software. So that's the type of thing that we look at in that 3530 course.
Did you know if there are any other Australian universities that would integrate this into IT or software engineering?
Not as far as I know, but you do tend to find it in the business, IT, information technology side of things. So at ANU, we've got a bit of an unusual arrangement in that software engineering and advanced computing and those sort of more technically oriented aspects of computing are within the research school of computer science. But we also have an IT degree being run out of the College of Business and Economics. Now those guys do a lot of our systems thinking systems, modelling, analysis, that kind of stuff. And I think that's probably fairly typical. I mean, there are really two sides to this course. And one is this systems thinking idea. That's a core thread through it. But there's also the idea that software engineers are engineers, right? And they need to develop the culture of being an engineer. And that, it's drawing on knowledge, synthesising and solving problems and addressing problems. So the course serves sort of both those purposes. And as Damien said, and a lot of us agree that it's a bit late in the program in year 3, right? We used to do this stuff in 4th year, sort of through the projects, but we're trying to get it back and develop what we want to see, what we want to produce are graduates who understand what engineering is and who work with other engineers. At the moment, before this course, I think we were producing people who were technically competent in computing, but really weren't engineers. And that's what we're trying to change. And I think that's fairly typical of most people.
How do you deal with the perception that some of the more technically focused software engineering students have that, all this kind of management stuff is, soft, that's not what I came to uni to do. Like, how do you manage, how do you give them those expectations and teach them that it's actually important to them?
It's a good question. First of all, I would say that this is not management stuff. We don't do any management in this course.
But we do. But you're right, though, that is definitely perception, because we do take project management in the software engineering degree.
Yeah, but not in this course.
Not in this one here, though, yeah.
But yeah, look, it's a good question, and it's a debate that's been ongoing. Just pick management, for example. When I did engineering, we didn't do project management, and I don't think we should be doing it now. Because you're not going to manage projects for another 10 years, right? It might be good to give you a bit of a feel for it, but I don't know that you should be expected to be competent project managers as undergraduates. But getting back to the question, I think a lot of it's to do with maturity. When you're, I was the same when I was doing my engineering degree. All I wanted to do was all the techo stuff. I couldn't care less about what was going on elsewhere. I just wanted to do the technical stuff. And it was only years later when I was out in the workplace and started to realise that what I was doing only had value if I could connect it somehow to the context. There's no point building the world's greatest bit of software if it's not used or if it doesn't do quite the right thing. The only way to know whether it does the right thing and to get it used is to interact with that broader context. It's as simple as that.
So systems thinking requires maturity first?
No, I think Damien alluded to this before. It's some people will get it and some people won't. Right? It takes different amounts of time. And maturity is probably not quite the right word. It's probably exposure to the idea over a period of time. That's more the point, I think.
And as you were saying before at the start, if you put systems thinking right at the start, basically some people, I know a lot of people that go into these degrees having wealth of knowledge already, but people come into a degree with no technical knowledge at all, and saying, okay, apply all this knowledge and ideas together. How can you do that if you don't know anything?
Well, you don't need to do systems thinking in the context of software engineering right at the start.
Yeah.
I mean, there are programs in the US where they introduce these ideas to primary kids.
Yeah.
Right? And it's just about thinking about the role of something. You pick, it might be just a sandcastle or something. Why is it there? What's its purpose? Yeah. Right? And just get kids to start thinking about it. It's not about how fancy the sandcastle is. It's, why are we producing the sandcastle? It's to have fun, waste the time, whatever it has to be, right? But there's a purpose. It's about getting people to think about the purpose.
Isn't the CARO built the review of their primary education scheme in Australia currently discussing integrating systems thinking into K-12?
I haven't heard of that. So you're saying they are thinking about it?
Well, one of the reviews I saw was systems thinking introduced very early stages.
Oh, that's interesting. It certainly has been talked about. for a long time. And if you Google systems thinking K-12, you'll get lots of that sort of stuff. And there are parts of the US where it is part of the curriculum, but there are other parts where it aren't yet. It's one of those funny things. It's systems thinking is sort of, you can sit here today, if you haven't heard that, you say, yeah, it sounds reasonable, right? But it's one of those things where, if you've got time here and understanding, it's like, I don't get it. And then all of a sudden something happens in your life, or something changes, and all of a sudden it's bang, the light goes on, and it's like, I get this stuff now. And because it's such a simple idea, it's almost trivial, almost like, what is the idea? What's the difference between the way I do it now and what you're saying? And then when you first exposed to it, it is like that. It's like, why am I, listening to this stuff? It's a no-no, it's obvious. But as Damien said, it's actually a lot more difficult to apply properly and to really get it. And it is this lifelong learning thing. Eventually, bang, the light goes on. And you can see it in the course. You can see students at the start of the course just, it's from this and this. Then all of a sudden their eyes open up and they seem a lot brighter and a lot more engaged because obviously they've got the message. It's so to understand. And then when you have people from, every week there's a different person from a different company or a different industry or a different, from a government department or whatever, coming basically to talk about, say, some technical requirements or architecture or whatever. But there's this flavour you can see through it of the big picture. And the involvement of people. As soon as you start talking about people involved in those things, it becomes a systems problem. And people start thinking the right. So maturity wasn't the right word. It's more, I guess it's age length.
Some of the work that you've done with WhatsApp, with ecology, some of the consultancy projects, with the main projects.
What am I doing? Yeah. Okay, so some time ago, my research originally, and still is to some extent, is on model-driven development and the belief that the current approaches that software engineering advocates for model-driven development, UML, model translation, is just all fun. I think it's just nonsense. It has never really worked. The researchers are all busy researching the hell out of it, but not getting anywhere. I think the fundamental reason for that is that we don't use models the way everyone else uses models. We use models as specifications, and I think that's wrong. Other people use disciplines like science and medicine and so on, use models to understand stuff. They build models to explain, to communicate, to explore, to evaluate possible scenarios, that kind of stuff. So my research has been on about using models within software engineering in that way. Now, as part of that, I've got this view that we should be building what I call domain models that are autonomous from other domains. So you have a model that describes how we do security, for example. Another one that says how we do traffic management or whatever it happens to be. And then separately from that, building another set of models that brings the knowledge together to specify something. And that's what engineers do, right? We've got all this knowledge out there in multiple domains, and our job is to bring it together. So I'm producing a systematic framework in which to do that. Now, some colleagues who we were doing the industry projects with, and some of the industry projects are actually with other disciplines, other labs around the university. And we were doing a project with a group of Defence School Environment. And I got to know these guys, they got to know what I was doing. And the project got kicked off called 3 Worlds. It was funded by the French Agency of National Research. We got about $1.2 million. And the aim of that project was to develop a new way of building ecological simulations, or simulation systems, models. And the key aspect of that was the idea, from the ecological perspective, that all ecological models draw on 3 main disciplines. Biology, reproduction, dispersal, that kind of stuff. Physics, exchange of gases and fluids and properties, and geometry, topology. So it was just a natural fit to the work I was doing, right? We've got these 3 domains. In fact, that's what's called 3 worlds, but of course there's more 4 worlds in that, as it turns out. And a systematic way of joining together. So that's how I got involved with ecologists. And since then, I've become interested much more generally in the idea of multi-disciplinary research. There's a whole field of doing research in the multi-disciplinary space. And one of the difficulties with all of that is that you run up against major obstacles within the academic environment. It's not set up to do multi-disciplinary work. I've got 3 PhD students who are across disciplines, and it's tough. It's tough for them, it's tough for me. Where you publish, who gets the money at the end of the day, who's going to examine this stuff, right? So I've got in ecology again. So one of my PhD students is applying this stuff, systems engineering, systems thinking, to the management of nature reserves. Now, who is going to examine that? So it's tough, but it's fun, it's enjoyable, and it's actually delivering real value. I don't know whether you saw Pascal's talk yesterday. Similar sort of array. He's taking stuff and applying it to real problems and systems new to that kind of work. And it's where all the fun is. The fun is in the boundaries. It's not in, to me anyway, it's not in all that stuff we have in the novels. We already know that stuff. Right? We know how to design, we know how to program, we know how to do all that stuff. What we don't know is how to bring it together in a more rigorous, systematic way. That makes sense. So, anyway, this is the whole course. So.
Any more questions? Where would you like to see more software engineers go to when they're applying systems? Like, what do you see future research involving software engineering systems?
I think generally that idea of computing and software being an enabler. So one of the things I keep on saying to people around here is that there's a lot more computing at ANU going on outside of our college than in it. And in fact, a lot more advanced computing. There are people building very sophisticated software systems in all sorts of areas, not just environmental science, but in epidemiology and in the social sciences. They're building very complex software systems, and they're doing it without any software engineering in sight. So that's another research project we've got going at the moment, is how is that? I happen to think that Sweetblock and all those things, all those software engineering textbooks, a lot of it's actually wrong, right? Because people are able to build these big complex systems. The climate models and so on, they're able to do it. Yet they don't see a lot of those bugs, right? And I think it's a bit of system stuff we're talking about. There's an element of that, and that those bubbles are all well defined, and they can just sort of draw on them. But I think also there's something a little bit askew with what we're doing in software engineering. So I think the future for software engineering research is in looking in those boundaries, looking at the role of software engineering in other disciplines. And the other thing we do, we call it software engineering, but all this applies to computing in general. Right? It's not just software engineering. I think it's computing in general. All right, Denise, thank you for the question.
I think you've fielded a lot of it. So that's
You're working with the VPAT. How's that applying to your study? Is that helping you develop that kind of systems thinking to your study as well?
DPAT is interesting. The probably the most applicable part of it is that because it's foreign affairs, they have a global network, and so when you build a system, there's 2 parts of that. One is that you have to make sure that it works across the world. So, taking into context, if you build something here, does that mean in Port Moresby or Manila or somewhere, are they going to have the resources to run that? And the second part of that is you have to think about, and this is something that I definitely would never have considered while just being a student at ANU, is that building software, for example, some of the things that we're building at the moment, has political repercussions. So things like, for a diplomat, if we are using, say, a visitor system, and so they're having people come into their embassies, other diplomats, and they have to use our system. If we build a crappy system, that has repercussions for our reputation as Australia. And that's something that, as a software engineering student, like that never would have crossed my mind. It wasn't until, they say, okay, you have to build this, but you have to understand there are all these other factors involved, and that it sits in context. You're not just building a visitor management system. So there's stuff in that definitely has opened my eyes, and it's also things that I would never have put those two things together without sort of having been introduced to the systems thinking. So if I hadn't seen, this is what systems thinking is, and this software has context, then when building software in the workplace, I probably wouldn't have asked, well, if this is a concern, what other political concerns do we have? What other restraints do we have? What other things do we have to take into account? Because it's all well and good to make sure it works on my laptop, but if it doesn't work overseas, then it's not much use to anyone. So there's definitely stuff in that's been interesting.
That's a good point. So just one more thing. So just a plug. So if this stuff sort of interests you, if you're an A&E student, you take the course. It's mandatory for software engineers and advanced computing students. But if you're a VIT student or any other student, you're welcome to join us. But if you sort of feel that this is something you're interested in, another thing to look at for certainly for A&E students are Vice Chancellor's courses. So the Vice Chancellor's courses, for those that don't know, are courses that are open to every student on campus. Anyone can. We have lawyers and artists and sociologists and scientists and computer scientists, and everyone can join this course. The one I run is called Unraveling Complexity, and in that course you have the opportunity to work in small groups, multi-disciplinary groups. So there's always a lawyer, because we have a shitload of lawyers in the world. There's always a lawyer. But typically there'll be some sort of theoretical guy, like a physicist or a computer scientist or something like that. There may be an art student or an anthropology student, something like that. And we give them complex problems to look at. And we expect those students during the semester to come up with some sort of intervention, something they can do to make a difference to that problem. So last year we had students looking at breastfeeding, disability, how do people interact with people with disabilities. We had internet privacy, it's a more technical one.
Government corruption, that was my group.
Yeah, that's right. Yeah, a whole pile of different topics. And it's the same sort of feel that we've got in this course, the stuff we're talking about here is applied to software engineering, but at that next level up. It's the same sort of culture we're trying to get into people, and a number of software development types have done that course. And I don't know, did you get something out of it?
I think the biggest thing I got out of it was just a sense of perspective of how other disciplines can actually contribute. Actually just trying to understand that people have other perspectives, and you need to take them into account.
That's right. And they're not all idiots, right?
Yes, which is something that a lot of engineers and science people have a bad habit of doing in their undergraduate years. Look at that poor art student, they're never going to get a job.
But those art students have got some very solid ways of thinking about ambiguity and uncertainty and so on that we don't. So we have panellists coming along talking about complexity from all sorts of perspectives: historical, art, math, what else do we have? Human psychology, a whole pile of things. So it's this course that zoomed out. So if you're not at ANU, okay, so I'll hang around a little while, and Damien and I will be here if we want to have a little bit of chat. Okay?
Cool.
Thanks a lot.
CompCon would just like to thank you two for doing this actually very interesting talk, and we have something for you.
Thank you.